I will try to make this as quickly as quick as I can. So first, we talked about the Unit 2 Worksheet 1. And so I'll kind of go through this quickly. You might need to write down or type some of the things that I'm saying. If you didn't have exactly what I'm talking about for these. And then we talked about some other stuff, took some notes down. And so I'll have a picture of that as well on the on Classroom. So anyway, number 1, you decide to boil water to cook noodles. You place the pan of water on the stove and turn on the burner. How does the behavior of the water molecules change as the pan of water is heated? Well, I would say number 1, the water particles are gaining energy, number 1. Number 2, that means they're getting faster, right? Which means the water is getting hotter. That's what's happening. It's heating up, right? Gaining energy. They're moving faster, which means they're getting hotter. Now, some folks said, well, that means the particles are getting further apart, and that's true. But can you notice the level of water in the pan rising as it gets hotter? Probably not. You probably would never notice that unless you knew that that water was going to expand from getting heated up. Not enough to notice, really. Now, part B, what about your answer would change if there were more water in the pan? Well, nothing about what I just said would change, I don't think. Are the particles of water still going to be gaining energy from the burner? Yes. Are they going to be moving faster? Yes. Are they going to be getting hotter? Yeah. Will they get further apart? Sure. So all those things are going to happen. So what is going to be different? The fact that there's more water. So more energy is going to be required because there's more what? More particles. If you got more water in the pan, that means more particles. More particles means it's going to take longer because more energy has to be absorbed. I don't know if I may have paused or not. Ooh, thanks, man. Let's see. Does this thing pause? I can't tell if this thing's pausing or not. I don't even know if I'm still recording. So anyway, I'll just pretend I'm still recording. I tried to hit the pause button. I don't know if I hit pause. Let's see. If I hit that again. Ooh, I was able to pause there for a second. I hadn't paused until I just, oh my gosh. Anyway, so there you go, folks. It's going to take longer. There's more particles, which means it's going to take more energy, which means it's going to take longer. But it's the same process. All right, number 2. What property of matter best describes the way a typical alcohol thermometer works? Explain in terms of energy transfer why alcohol level in the thermometer rises or falls when you place the thermometer in contact with both warmer or colder objects. Now, I'm not sure if you even know or understand what an alcohol thermometer is. So let me grab one. Maybe you were confused by the fact that I specified an alcohol thermometer. This is an alcohol thermometer, okay? This is the kind we would use in the classroom. There is red liquid in here, and there's a little reservoir at the bottom, and then there's a tiny little passageway, and of course you can see the numbers then on the, oh boy, let's see. You can see the numbers on the scale that would tell you what the temperature is as that red liquid would rise or fall inside this tube. So that is an alcohol thermometer because the stuff in here is actually alcohol, right? This is not mercury. Every year I ask students, hey, what is the stuff in this? And they say, oh, it's mercury. Mercury's not red. Mercury is a silver metal. This is a red liquid. So this is a mercury thermometer. And Again, it looks like that's a metal tip there, but in reality, it is a glass. This whole thing is a glass vessel, and that's a little reservoir where the mercury is. And then you can see inside, hopefully, well, maybe you can see, oh my gosh, how close can I get here? That tiny little narrow passageway, that's where the mercury is going to rise and fall. Let's see, where is it right now? Where is it? Oh, look at that. It's about 23, 22 and a half, maybe, degrees Celsius in here. Well, after I was just putting my finger on it, maybe it warmed up. I don't know. So anyway, that is a mercury thermometer. I'm asking about an alcohol thermometer, which is the same principle, but the stuff inside is alcohol and not mercury. So anyway, what property best describes how this thermometer works? Well, I hope the two terms you're thinking are expansion and contraction, right? Expansion and contraction are how this thing works. Now it says explain in terms of energy transfer. Well, if you put the thermometer in something warm, what's happening? Well, the particles of the alcohol here are gaining what? They're gaining energy. And that means they're moving faster. And that means they need more space. And that means they get further apart, which means the stuff expands because the particles got further apart. Where is the only place the stuff can go? Up the tube, okay? That's for when it gets warmer. Now, when it gets colder, if you put this thing in something that's colder, then what's happening? Energy is being taken away from the alcohol. The particles are getting, so energy is taken away. The particles get slower. They need less space. They get closer together, which means the level falls. So those are kind of the steps involved. The energy transfer. Energy is either being gained by the alcohol, which makes them faster, need more space, get further apart. The alcohol expands. Or energy is being taken away from the alcohol when you put it in something cold. Particles get energy taken away. They move slower. They need less space. They get closer together, and the alcohol level drops. Hopefully that makes sense. Number 3, if you are feverish, why can't you take your own temperature with your hand? So you can't be like, oh, I think I feel warm. I think I have a fever. Because it's your own body. You can't tell how warm you are with your own body. You could put your hand on someone else and think, whoa, that feels warmer than my body temperature, so they might have a fever. So very difficult to tell your own temperature with your own body. Our bodies are really good at sensing differences in temperature, not at actually telling the temperature, but noticing a difference in temperature. So if you were to put your hand on your own face and then someone else's, you could tell a difference there, but not your own hand on your own face. That's not going to help because it's your own body. Number 4, describe how Anders Celsius devised a temperature scale that bears his name. Well, remember, he took a glass tube similar to this with some mercury in it. He put it into freezing water and he marked it as what? 0 degrees Celsius. Then he put that same glass tube in boiling water and it went, and the mercury expanded and it rose up to a certain level. And he marked it and he called it what? 100. That was it. He made it up. He used the freezing point and the boiling point, and he marked 2 places on a glass tube and said, this one's 0, this one's 100, and then he divided it up into little degrees and said, okay, that's my scale, and I'm going to name it after me. Moving on. Your older brother announces that the lid to the jar of pickles from the refrigerator is impossible to loosen. You take the jar, hold the lid under the hot water from your sink's faucet for a few seconds, and calmly open the jar. Your brother, when faced with this blow to his pride, claims that he loosened it for you. What knowledge of materials have you applied in this situation that really explains how you were able to open the lid? Well, there's a couple different things here. What is the lid made of? Typically, if you have like a jar of pickles, do you know anything about a pickle jar lid? They're usually metal. The lid is metal. The jar is glass. Metal is a good what? Conductor of heat. Glass is not. It says you take the jar, hold the lid under the hot water from your sink's faucet for a few seconds. What's happening to the lid of the jar when it's held under hot water? The particles get faster, need more space, the lid expands. It won't fit as tightly because you're making the lid expand. And the lid will expand way faster than the jar will. And you're not putting the whole jar under the hot water, it's just the lid. So you're using, what knowledge are you using about materials? You are using your knowledge of expansion and contraction. You're making the lid expand so it fits more loosely so you can easily twist that lid off. Hopefully that makes sense. Now, number 6, I said not to do because we haven't seen that yet. We will look at that eventually. Now, number 7, define the following: evaporation, condensation, melting, freezing, sublimation. And I forgot to put deposition on here. So maybe we should add deposition. So evaporation is again from a liquid to a gas. Condensation is when things go from vapor or gas down to a liquid. Melting is when things go from a solid up to a liquid. Freezing, when things go from a liquid state down to a solid state. And sublimation, when things go from a solid state all the way up to a gas state. And then deposition, when things go from a gas state all the way down to a solid state. Now, describe the particle behavior in the following states of matter. So again, like we had said in the notes, solids, the particles are stuck in a rigid structure. They can't go anywhere. They can only shake and move a little bit, vibrate and shake back and forth. Now they can get fast, but they can't go anywhere. They're stuck in place. They have no freedom, no ability to go anywhere. Liquids, the particles now have broken the structure. The structure has fallen apart, and the particles can kind of move around, and they can meander, and they can slip and slide past each other, and they can get around the rest of the particles. So they have some more freedom. The structure's fallen apart. They can get around a little bit, slip and slide past each other. And then, of course, the gases, the particles in the gas, they are free to do anything they want, go anywhere they want, complete chaos. They're far apart, and they have total freedom. Now, rank them from highest to lowest energy level. Well, I hope from the sounds of it, you can tell that solids, the particles in a solid would have the lowest energy level. Liquids would be a step up from that, and then gases would be a couple steps up from that. So that was that. We talked about this assignment. We'll come back to this and we'll get 6 here at some point. Then we started talking about this stuff. And again, this is, I posted the notes page here, but we were talking about temperature and how temperature is, oh no, I'm in the way. Oh no. You can't see the end of this thing. Hold on, let me move this. Oh boy, oh my gosh. Let me move this over this way because my face, there we go. So temperature is the measure of how is the speed of the particles or the average kinetic energy of the particles. Here's the thing though, these thermometers, these things don't tell us how fast the particles are. They don't tell us how fast they are. What do they tell us? We actually measure how much the substance expands or contracts, which depends on how fast the particles are. So all this is telling us is how high or low the stuff goes in the tube, how much it expands when it's hot, how much it contracts when it's cold. They don't actually tell us how fast the particles are. How fast the particles are, though, is what temperature is. We can't measure that directly. We can measure it indirectly by measuring how much the stuff expands or contracts inside this glass tube, which is strange to even think about. Then I talked about temperature scales and how Fahrenheit's temperatures for freezing and boiling are strange, 32 and 212. It's kind of weird. Celsius, 0 and 100, because again, that's what he decided. He said he was going to make 0 when water freezes and 100 when water boils. Now, this absolute zero thing and this Kelvin scale. The Kelvin scale is known as the absolute temperature scale. There are no negative temperatures in the Kelvin scale. 0 in the Kelvin scale is 0 temperature, like no temperature. Now, time out here. If temperature is the measure of the speed of the particles, if you have 0 temperature, what do you have? You have 0 speed of particles. If you have 0 speed of particles, then we're saying the particle stopped moving. But what did we say? Hold on. Oh, I'm in the way here. So what did we say? Oh gosh, I am in the way. Can I move this down here? What did we say before? We said all matter is made of particles and that these particles are in constant motion. This is saying that, that if we get to this thing called absolute, now I'm in the way again. If I get to this thing called absolute zero, that's the temperature at which the particle's motion stops. So the particle motion stops at 0 Kelvin. There's no negatives. And that means we have no temperature at all. Which, if we look at this, my goodness, that's cold. I mean, negative 460 Fahrenheit, negative 273 Celsius, that's cold. Like, there's no place on the planet that's that cold. And can we actually get matter to be that cold? We can't. So it can't get down to 0 Kelvin. The motion of the particles don't stop. They don't think it's possible to even get that cold. We've gotten close, but we haven't gotten all the way there because the particles can't stop moving. At least that's what we think. Then I talked a little bit about Daniel Fahrenheit and how his scale was set up. And apparently he decided that 0 Fahrenheit was going to be the freezing point of salt water, or the temperature that you get when you put salt on ice. If you didn't know that, if you put salt on an ice cube, the temperature actually goes down. The melting of the ice requires energy, and the salt speeds this process up, which means heat gets brought in from the outside, which makes it feel cold. It seems odd. It's called endothermic. It's an endothermic process. It's not a chemical reaction because we're not getting any new substances, but it is an endothermic process. And so, anyway, when you put salt on ice, it gets cold. How cold? 0 Fahrenheit. So Daniel based his 0 on that. Then his 100 Fahrenheit, he based on the temperature of a sweaty man's armpit, or human body temperature. Kind of strange. So Daniel also used 0 and 100, but his 0 and 100 weren't the same place as Celsius's 0 and 100. And lastly, I talked about this little graph here. This thing right here, I did this not in class this year. This is a graph from years past. This right here shows, let me kind of explain what I did. I had a beaker of ice with a temperature probe in it. And it was on a flame, Bunsen burner flame, or a hot plate. I forget which one I used this time. And it was being stirred up. And if you'll notice here, the temperature at the very beginning here, it was not really going up. And then it went up, and then it stopped going up. So this is temperature on the y-axis. It's time on the x-axis. So this is how many seconds had gone by. So this is 500 seconds here. So almost 600 seconds here before it stopped going up. The temperature stopped going up altogether. Now, I sketched this graph here in the notes for this purpose. What was happening at the bottom part of that graph was melting. The ice was melting here. Here, the water was boiling. In the middle, the water was heating up. So I had asked everybody, hey, what is this graph telling us about the water that was, again, ice, and then like solid, right? And then a liquid. And then, of course, it's boiling, becoming a vapor. And so I said, what is happening during this process? And someone said that there's no temperature change. The temperature does not go up during a phase change. Now, a phase change is another name for a change of state, which boiling and melting are both changes of state. So during boiling or melting, there is no temperature change. The beaker was on the flame the whole time. The ice was gaining energy, but it wasn't getting any hotter. It was melting, but it wasn't getting hotter. Once it stopped melting, boom, then the water can heat up once it's in liquid form. Once it reached the boiling temperature, why didn't this keep going up? Because water can't be hotter than 100 Celsius and still be liquid at atmospheric pressure. So that won't go up anymore because you can't have temperature changing during boiling, which is a phase change. So we will talk more about that Wednesday or Thursday, depending on which block you're in. But that's what we had talked about so far today. So I'll have this video on there, and then a copy of the notes, the actual picture of this, and then, yeah, we are looking at a test on Friday for the B1 folks, Monday for the B2 folks. That's my plan would be at the end of this week, beginning of next week, again for the B1 versus B2. We're looking at a test on this stuff. So anyway, hope you're all doing well. Hope if you've not been here, you're actually watching these and you're getting something out of it, I hope. I'm sorry this was so long. Take care.